Alright, everyone. In the last video, what we saw is if we just make some reasonable assumptions, we can turn our regular non-ideal op-amp into an ideal op-amp. So this is how we define an ideal op-amp, just based on our reasonable assumptions. Nothing too complicated. And then using those assumptions, we found um, two important properties, or at least I've been calling these important, for now, for a while. But as we'll see, as we solve this problem, which is the same as what we did um, in the video before last, it was just we considered it as a non-ideal op-amp. Okay, this time we're gonna solve this problem, the same problem, but this time we're gonna um, you know assume that it's an ideal op-amp. Okay, treat it as an ideal op-amp and see how things go about. And one thing is, you'll see why these are important. And the other thing is that when solving, when you're using an ideal op amp, when you're assuming that an op amp is ideal, the way you solve the problem is a bit different than what we did with the non-ideal one. You actually don't need to, unlike what we did here, you actually don't need to break the op amp up. Oh, sorry. Uh, I'm sorry. You don't need to break the op amp. Wow, that's a tongue twister. Op amp up into its equivalent circuit portions. Okay, so these problems can easily be solved if you just apply circuit theorems and analysis methods on the nodes, or loops or other places around the op amp. Okay, yeah, in the places other than the op amp. There is no need to break this up, as we'll see. But anyways, enough with me just explaining things. The best thing to do is just to go on and solve it. Okay, so let's try to solve it. Let's try to solve it. And we're, as you'll see, we are going to use these two results quite a bit. Okay, so these two. So the first thing. Okay, so we have this problem. The first thing that we notice is, so this is our ground. Okay, this is our ground, and obviously this has a potential of zero, right? By definition. But this is this whole node, right? This whole node is the same. Okay, this is the ground, and this is this is your non-inverting input, right? This is your non-inverting input. So we have V2 equals 0 volts. But what did we say? If this is an ideal op amp, your non-inverting input and your inverting input, they have the same value. So if this is 0 volts, if V2 is 0 volts, lo and behold, your V1 also has to be 0 volts. I'll write that down. Your V1, which is here, but again, this is the same node, right? So this part right here, this whole node has a potential of 0 volts, just like our non-inverting input. All right, so that's good and all, but we also notice another thing. So like last time, if we just apply nodal analysis, or actually apply KCL here, okay, on this node. Okay, what do we see? So let's try to do that. I'm using green a bit too much. Let me use purple. Okay, so let's try to apply KCL here. Okay, so let's see. There's a current here. Okay, there's a current here entering this node. There's a current, let's say, exiting this node, and you could say there's a current here. Okay, right? There's a current here. But what did we say? What did we say before? This was another one of our conclusions, that the currents entering or exiting our inputs, okay, our op-amp inputs are zero, right? Are zero. So this current is actually zero, right? This current is zero. It doesn't affect our calculations, or we'll just put zero there. Anyways, so let's apply KCL here. So the current entering has to be equal to the current exiting. So this current has to be equal to this plus zero. Well, the zero would just disappear. So what we have is, let's see. So the current entering this one, okay, is what? Let's see. It's Vs. So this node, the value of this node is Vs, right? The value of this node is Vs. This Vs minus the potential of this node, which is what we found is zero, divided by 10 kilo ohms. 10 kilo ohms, 10 times 10 to the 3. Okay. This is equal to this is equal to the current exiting. Okay, so the potential difference is 0 minus what's the potential here? That's V naught, right? Same as here, right? This is the same node, this is the same node. Okay, so the current, and I'll do it in a different color. Let's see, I'll use this one. Okay, so let's say this one is here. So this is the potential difference, which is 0 minus V. It's not V naught, it's V sub O, output voltage, divided by our resistance, right, which is 20 kilo ohms, which is 20 kilo ohms. This one right here. All right. So that is 20 kilo ohms. 20 times 10 to the 3. All right. Let's multiply both sides by 20 times 10 to the 3. If we do that, what we get here is 2 Vs. Okay. 20 times 10 to the 3 and 10 times 10 to the 3. The thousands cancel out. 20 by 10 is just 2. And here this, and what we multiply cancel out. So what we have is minus V naught. And at the end, what we get is this is exciting. I think you should really be excited now. Even on this statement itself, we more or less got the result that we got before. After painstakingly doing the non-ideal op-amp calculation pretty easily here. It just took a few lines. And using some of our results, but we got our result already. I mean, we got our answer already, the closed loop voltage gain in that problem. So uh, as we see here, this was pretty easy to solve using our two properties. Um, uh, Assuming this is an ideal op-amp, we got the result pretty easily, and more importantly, actually equally importantly, I should say, is it's not just easy; it's actually very accurate also. Okay, it's very accurate here. As you see, the actual answer, the if you this answer I got right here. I didn't make any simplifications at all, anywhere. Even I didn't make any numerical simplifications, and this was the answer that I got. So this one is 100% accurate, and what we see is this is more or less -2. I mean, there's really there's so little of a difference, really, so negligible of a difference that yeah, this is you can just treat it as -2. There's really, you could say, no difference. So we got really the same answer. Okay, there's I don't even want to call it an approximate. It's really the same answer, you could say. uh, and we got it pretty easily, and that is why generally the notion of ideal op amps is so widespread, because they're not only easy to deal with, but for practical circuits where you're in your the linear region of your operating op amp, and your resistances are your resistances, as we saw previously, have these kind of, like, your standard is something like this, and the resistance, the two input and output resistance of the op amp are so far out from the standard resistance for and this is really the case for practical circuits that we use usually. So uh, under those conditions, the ideal op amp is really a very it's a very good approximate. It's a very good approximate, and it really gives our it's really easy to deal with, gives our answer pretty easily and accurately. All right, so I think I've gushed enough about that. Just one last thing, I think you should see this too. So here, as you can see, if I just rearrange this, I get my v naught is, we saw this before too, but well, we got this using the ideal op amp. Our v naught is equal to -2 times Vs. One thing is that suppose if you call this your supply signal, okay, then you see that your output signal is basically -2 times your supply signal. So here two things are happening. The amplitude, okay, or I guess I should say size. Okay, so the size of this is multiplied by 2, right? So it's amplified, that's one thing. But also, equally importantly, it's the polarity is reversed, right? The polarity is reversed here. Okay, So you have a negative sign here, or you could say, the way we have been calling this for op-amps, like the inverting inputs, because we make it negative before calculating the voltage differential. So same thing here. This is basically inverting your supply, right? It's basically inverting your supply signal, and that is why this op amp in particular, okay, it actually has a name. It actually has a name. It's a pretty common thing. You'll see, or as you'll study op amps more and more. This is called an inverting op amp, and this is what we're going to do in the next few videos. We're going to look at different types of op amps, like this one, and the summing op amp, the non-inverting op amp, and there are a few other kinds, and we're gonna discuss those one by one. So see you in the next video, and study smart.